Okay, so in this video we're going to talk about diffraction, and that's going to lead us into talking about the double slit experiment, and then we will be done with topic 4.4, which again is over wave behaviors. Okay, so diffraction is the last wave behavior that we're going to talk about. The double slit experiment, which you should be somewhat familiar with if you watched the original double slit experiment video from before, is historically significant because basically that experiment provided the evidence that light behaves as a wave. Okay, but we'll come back to that later. So let's talk about diffraction first. Make sure you don't confuse diffraction with refraction, which is another wave behavior. So basically, refraction is the wave behavior when a wave travels from one medium into another medium, and then it changes wave speed, which causes the wave to bend. Diffraction happens when a wave hits an opening or an object that's a similar size to its wavelength, and that causes the wave to spread out. Okay, and so just to give you an idea of what this might look like, okay, here we have basically a slit or a hole. Okay, so we basically have a wall that has a hole in it, and if we have a wave come in, when it hits the hole, it spreads out past the hole. Okay, and this spreading out is what we call diffraction. Okay, so you see the wave come in from the right, that's the incident wave. It hits the opening, and then the wave spreads out past the opening. Okay, in this case, it spreads out in kind of like a circular pattern. Okay, now the amount of diffraction basically has to do with how big is the hole relative to the size of the wavelength. If the object or if the hole, whatever is going to hit, if it's much bigger than the wavelength of the wave, then the diffraction effect is very, very small. So in other words, if I were to make this gap a lot bigger, the wave would not spread out as much. Okay, so you get the maximum amount of diffraction when the size of the object or the size of the opening is about the same size as the wavelength of the wave that you're trying to diffract. Okay, so again, diffraction is caused by a wave hitting an obstacle or hitting an opening, not to be confused with refraction, which is caused by a wave traveling from one medium into another. Okay, and then this picture is just kind of showing you some more examples of diffraction. On the left, you can see something similar to what we saw in the last slide. We have a wave coming in. These lines represent the wave fronts of the wave, okay, which would be where the crests or compressions are. And you can see when it hits the opening, here the opening is actually a little bit bigger than the wavelength. Remember, you can tell the wavelength by looking at the gap size between two wave fronts. So here I can actually see the opening is a little bit bigger than the wavelength. You still get some diffraction, but not as much as if the gap was smaller. And notice it doesn't have to be a perfect gap. If you look on the at the picture on the right, you can see a wave coming in from the left, and it hits like a corner of a wall, and it still spreads out around that opening. Okay, so this spreading out effect is what is known as diffraction. Okay, so here I'm going to link a couple of videos having to do with applications of diffraction. There are some interesting applications of diffraction. One of those applications is, or explains the reason why you can hear sound around a corner, but you cannot see around a corner. And the reason has to do with the wavelength. Okay, the wavelength of a sound wave in air is about 1 meter. That's roughly comparable to the size of like a wall or a corner that you might see in everyday life. The wavelength of light, visible light, is somewhere between 400 nanometers and 700 nanometers. And so the reason you can hear around the corner is because you only get diffraction when the size of the object or the size of the opening is somewhere close to the same size as the wavelength. Okay, so here you can see sound wave diffracting around a corner. There's a radio playing a sound wave. Because the wavelength of the sound wave is comparable to the same size as the corner of the wall, you get this diffraction effect. Okay, but because the wavelength of light is so much smaller than that, you don't really get a lot of diffraction, and so the student cannot see the radio around the corner, but they can hear it. Okay, there's also probably the sound wave also probably travels through the wall a little bit, but it can also spread out past the wall because of diffraction, as you can see. Okay, so here is another simple example. A person is walking along one side of a building, and a car is driving along another side of the building. The person can hear the car approach, but cannot see it. This is explained by the sound, or by the fact that sound waves, what? Okay, well, we're talking about diffraction right now, so clearly the answer is B, since it's having to do with diffraction. This is one of those questions, by the way, where you have to make sure that you answer the question being asked, because some of these are true statements. A is definitely true. Sound waves travel much slower than light waves. D is also true. Sound waves are longitudinal waves. All right, but neither of those answer the question. Okay, why can the person hear the car approach but they can't see it? Because sound waves diffract, and light waves probably don't diffract very much because of, again, it has to do with the size of the object that's being hit versus the wavelength of the wave. Now remember, any type of wave can diffract, okay, including light waves. But remember, you only get really good diffraction if the size of the opening is pretty close in size to the size of the wavelength. And so if you want to cause diffraction with light, you could do it, but you would have to have an opening that is very, 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 very small, because the wavelength of visible light is very, very, very tiny. But diffraction is a wave behavior, and any type of wave can experience diffraction. All right, so what is the answer to this question? Clearly D. I just said that. What wave behavior is being demonstrated here? Okay, so watch the animation. Well, that's clearly refraction. Okay, we saw a wave hitting a boundary between two media and then slowing down and bending. Okay, that is refraction, not to be confused with the diffraction, which we've been talking about. Okay, so just to go on a little bit, I do want to show you this. This is light being diffracted by a very, very tiny, tiny hole. And of course the hole has to be tiny because the size of the opening has to be, really small, relatively close to the size of the wavelength of the light. And what you actually get if you pass light through a tiny hole, you actually get something that looks like this. Yeah, you get these rings where you see, the bright middle part of the ring is really, really bright, and then you see a black ring, and then you see a light ring, and then you see a black ring, and then you see a light ring. Okay, and it would look something like this if you were to graph the intensity. The reason you see this, by the way, and as we'll kind of talk more about later, but this actually has to do with interference, because what happens is the wave diffracts as it goes through the hole, and as it diffracts, every point along the wave actually acts as a new source of a wave. And so when you get different wave sources, they can interfere with each other. And so what you're seeing right here actually is an interference pattern. Okay, wherever you see darkness, you see destructive interference, and wherever you see a bright spot, you have constructive interference. Okay, so that is diffraction. Okay, so now we're going to talk about the double slit experiment. Okay, actually, before we talk about the double slit experiment, why don't we go ahead and end this video here, and I will do a separate video just for the double slit experiment. Okay, so please let me know if you have any questions about diffraction, and I'll see you guys in the next video.